So good morning once again. So in this video I want us to begin by looking at what we call the first order linear equations, and by doing this we want to see how to solve such differential equations. So how does a first order linear differential equation look like? So we begin with our first definition, where we say that a first order differential equation is said to be linear if it takes the form. I want you to critically look at this form in equation 2.11. So the form is a1 of x dy dx plus a0 of x y equals to b of x. So this means that when you look at dy dx, its coefficient should be a function of x. Then when you look at y, its coefficient should be equal to a function of x. And when you look at what is on the right hand side, is also a function of x. So you have dy dx with coefficient of x, or this can be as well a constant. The a1 and the a0 can be constants or functions of x. If they are functions of y, I mean the a1 and the a0, then that differential equation is not linear. Okay? Or if this b of x is a function of y, then still our differential equation will not be linear. So a first order differential equation is said to be linear if it is of this form. You have a coefficient of x dy dx plus a coefficient of x y equaling to b of x. Okay? Okay. Now, let me first put the pen and show something to you. So, what if we decide to divide throughout by a1 of x? This equation 2.11. Even this side, divide by a1 of x. And even on the right hand side by a1 of x. So what is going to happen is that this a1 of x and this will cancel, so that will remain with dy over dx plus, now we shall have here a0 of x over a1 of x y. So you should note that this a0 of x over a1 of x, both a0 and a1 are functions of x. So we can decide to call this coefficient p, capital P of x. So it will still be a function of x. When you have a function of x divided by a function of x, you get a function of x. So I'm just calling that function capital P of x, y, equaling to b of x divided by a1 of x. Still, these two are both functions of x, so you can decide to say that, okay, after dividing them, suppose we get something like q of x. So take note of this differential equation now, because it is the one which is going to lead us to the method that we use for solving such first order linear differential equations. Okay? So if you have a differential equation of this form, dy dx plus a function of x times y equaling to a function of x. How do you solve that differential equation? Okay, so the equation I've just written is this one in equation 2.12. Okay, so this is the differential equation that we have. So we just divide throughout the equation that we have in 2.11, and we just divide through by a1 of x, a1 of x, a1 of x, and then we say let a0 of x over a1 of x to be p of x, and let b of x over a1 of x to be q of x. Okay, where the p and q are either functions of x or constants. So these should be a function of x or a constant. The same applies to q. Q can be a function of x or a constant. If it's a function of y, if p is a function of y or q is a function of y, then this differential equation will not be linear. Actually, in this example here, they're just trying to give examples of a linear first order differential equation and nonlinear first order differential equation. For example, in this first example here, by the way, I think this was a mistake. This bracket here was supposed to be here, so let me try to correct it. So it was supposed to be something like this, and then this one is off. Okay, yeah, such that you have x squared sine of x minus cos x y equaling to sine of x dy dx. So we are saying that this equation can be written in the form a1 of x dy dx plus a0 of x y. Remember, this is the definition that we gave when we said a function is linear and first order, equaling to b of x. How can we write this? So you can see that if you begin with this side and you say you have sine x dy dx, this will be the same as having a1x dy dx, and then plus. So realize that when you take this minus cos x y this side, you have plus cos x y equaling to, so this side you only be left with x squared sine x. So when you look at this form, this differential equation, and you compare it with the definition we had in equation 2.11, realize that indeed this is linear, because this is a function of x dy dx plus this one is also a function of x y equaling to the entire x squared sine x is also a function of x, which is the b of x. So example 1 is a first order linear differential equation, while if you look at the second one, you have y dy dx. This y here is not a function of x, so automatically this disqualifies this second example from being linear. Also, when you look at this next one, you have sine x. Okay, that is fine, this is a function of x, but now this is y cubed, and yet the definition says a0 x y. So because of this y cubed, then this will not be linear. Otherwise, this side, the right hand side, is okay because e to power x plus 1 is a function of x. But because of this y, which by definition should be a function of x, and because of this y cubed, which by definition should just be y, then example 2 is not linear. Okay, now we've already looked at how we get this 2.12 by dividing throughout by a1x, 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 and then we say that let a0 x over a1x be capital P of x, and let b of x over a1 of x be capital Q of x. So if you have a differential equation of this form, how do you solve it? So that now leads us to our next method of solving differential equation, and that is the method of the integrating factor. So when we want to use the method of the integrating factor, we look at differential equations of this form in equation 2.12. So I'll not take you through these details of how the formula for the integrating factor comes about, but what I want you to note is this. Where is it? Where is it? Where is it? Where is it? Okay, it is here. That, how do you find the integrating factor? The integrating factor, you should just take note of this. Maybe in the future when you want to do research in differential equations, then you can go through the details of this proof. But for now, let's not go into the proof of finding the integrating factor. I just want you to know it, that the integrating factor is given by this formula. It is exponent raised to the power integral p of x dx. So given a differential equation, identify your p of x, okay, and then you find this expression e to the power integral p of x dx. Okay, let's look at an example. So if you look at this first example here, you have dy dx plus 2y equaling to 3 e to power x. So this is a first order linear differential equation because we have this form. Don't forget, dy over dx plus p of y equaling to q of x. Okay, remember we said that this p can be a function of x. The same applies to q, or they can be constants. So in this case, if you compare these two equations, you realize that dy dx, that is okay. Plus, that is okay. P of y, here you have 2 of y, so that means p corresponds to 2, and then this y corresponds to that. Okay, so that means using the formula for the integrating factor, which we said is the same as exponent to the power integral p of x dx, our p is 2. So that means the integrating factor will be equal to exponent integral 2 dx. Okay, so this will be the same as exponent. What do you get when you integrate 2 with respect to x? You get 2x. Okay, so that is the integrating factor. Now what happens after finding the integrating factor? The next step after getting the integrating factor is to multiply that integrating factor through the given differential equation. So our integrating factor in this case is e to power 2x. So let us multiply e to power 2x throughout this equation. Okay, So what shall we get in that case? So when you multiply e to power 2x, then you are going to have e to power 2x dy dx plus here we shall have 2e to power 2x y, okay, equaling to e to power 2x times e to power x, that will be e to power 3x times 3, so that will be 3 e to power 3x. Okay, then after multiplying the given differential equation by the integrating factor, you look at the left hand side. Okay, this left hand side in most cases is a result you get after differentiating some function. For example, I want you to note that, for example, this left hand side here was got by differentiating e to power 2x y, which is here. I want you to use product rule, differentiate this. You realize that it will give you e to power 2x dy dx plus 2 e to power 2x of y. Okay, so always take note, whenever you finish multiplying the given differential equation throughout by the integrating factor, try to think of which function was differentiated to give you this term or expression on the left hand side. So at this point, your knowledge of differential equations, rather differentiation, product rule is very, very important. But with practice, you realize that you can easily guess the function that was differentiated. So after identifying which function was differentiated to give you this expression on the left hand side, then we write it. That's why you have that d dx of e to power 2x y. So this is now representing the left hand side is equal to 3 e to power 3x. So at this point, multiply both sides by dx, even this side by dx. So when you do that, you remain with d of e to power 2x y equaling to 3 e to power 3x dx. Okay, then at this point, integrate both sides. Integrate both sides. D of this term will give us this term. Just like how you have d of x and then you integrate, you get x. So d of this term will give us e to power 2x y equaling to integral of 3e to power 3x. By now, I'm very sure you know how to integrate. Okay? How do you integrate an exponential function? You first differentiate the power. So when you differentiate 3x with respect to x, that is 3, and then you divide by the power, the differentiated power. So that means in this case you have 3 over 3 e to power 3x, which will give us e to power 3x. I don't want to go into the details of integration, differentiation, because I'm sure these are basic concepts which you should be knowing by now. So since we are integrating, then we just add a constant. Okay, but what do we want to get? we want to get y, the value of y, because we had the y, the x. So to get y, that means you divide both sides by e to power 2x. Even this side by e to power 2x. And this side by e to power 2x. So this e and this will cancel, so that you remain with y equaling to, what do you get when you divide these two? Since they are the same bases, we subtract the powers, so you remain with e to power x, then plus c over e to power 2x, the same as having c e to power negative 2x. And so this will be our final solution to this differential equation. So as simple as that. So this is how we use the method of integrating factor. We use it to solve differential equations which are in this form. That is, they should be first order linear differential equations. Okay, so there is another example here. Though in this example they gave us the original condition, and when you look at this example, 1 over x dy dx minus negative 2y over x squared equaling to x cos x. So realize that this is a function of x, negative 2 over x squared is a function of x, 1 over x is also a function of x. But remember, we divided through by a1 of x. So that means we need to make sure that this item here, 1 over x, disappears. And we can only do that by multiplying throughout by x. So you multiply by x here, you remain with dy dx minus negative 2 over x squared times x times y, that will give you 2 over xy. Then if you multiply by x this side, you have x squared cos x. So this is now the differential equation in the form dy dx. Let me try to write. In the form dy over dx plus p of y equaling to q of x. So when you compare these, you realize that your p will be negative 2 over x, and hence the integrating factor will be given by exponent integral of p dx, where p is negative 2 over x. Okay, so what happens when you integrate negative 2 over x with respect to x? You end up with negative 2 natural log of x exponent. Okay, and this simplifies to 1 over x squared. Okay, then you multiply throughout. You multiply this differential equation by 1 over x squared. So don't ask me how this comes about. Now this is knowledge of logarithms. I want you to figure out how e to power negative 2 natural log of x becomes 1 over x squared. Okay, yeah, there are some rules of indices that this negative 2 can come this way on x, and then you have e to power natural log of x to power negative 2. The e and the natural log will cancel, and you know that x to power negative 2 is the same as 1 over x squared. So those are rules of indices which you must have come across before. So if you multiply this equation throughout by 1 over x squared, which is our integrating factor, then you end up with this. And then look at the left hand side. What was differentiated to give us this term on the left hand side? So realize that what was differentiated is 1 over x squared y. When you differentiate this using the product rule, you get this term on the left hand side. So that's why you have that d dx of 1 over x squared y is equal to cos x. Multiply both sides by dx and then integrate. Okay, so you're going to end up with 1 over x squared y equaling to, you integrate this with respect to x, you end up with sine x plus a constant. But now this time we have an initial condition that when x is pi over 2, y is 3. So this initial condition, as we saw in the previous videos, helps us to find the value of this constant. Okay, so when you substitute x pi over 2 and y as 3, then you're going to realize that your c will be given by this 12 over pi squared minus 1. Please, I want you to try this out. I don't want to spoon feed you, giving you, when you do the things on your own and you find these values on your own, you feel more satisfied and more happy. Okay, so don't just follow the videos, but get a piece of paper and try out each and every step. That's when you learn more. So after getting your c, then you substitute in this equation and then make y the subject of the formula, and you're done. So as simple as that. That's the method of using the integrating factor to solve first order linear differential equations. Take your time, go through these two examples, discuss with a friend, make sure you understand, and then after, you can now embark on trying these exercises. I'm going to give you an assignment, but the questions in the assignment are going to come from these exercises. Okay? Yeah, so I'll stop this video at this point. See you in the next video.